Yes, I'd like to tell you a little bit about the Order of the Engineer. It's got a great history, and I think as part of the history of the Order, we learn a lot about why it came about and why it's so important that you're all here today. And it's just amazing to see all of you here today. When I did the Order, I think there were like 11 people in the room. So this is a huge accomplishment, and I just love to see everybody here. So a fundamental part of the Order is a progression from academics to engineering practice. And it's a transition from learning to reality that requires clear vision, understanding of what we've done in the past, and what we must continue to do for humanity to improve the quality of life everywhere. So as engineers, we all owe a huge debt to our profession. The credibility that we have out in the world today is a direct result of the people that came before you, the people that essentially you'll be replacing and taking over. It's in your hands now to keep that credibility strong. It's incredibly important. As we meet the needs of the future, we look to you, the engineers of the future, and place our faith in you not only to rescue the environment, but also to help bring about unity that can bode well for the entire spectrum of our profession, which we have to maintain ourselves and the public that we serve. As engineers, we have a responsibility to become licensed. So I really want to entice you to seriously consider becoming a licensed professional engineer. If you think about it, doctors have license, accountants are licensed, we have lawyers who are licensed. Part of the licensing process is certification, that not only have we done the studies, but that we have met the standards of our society, and that we have continuing education requirements, as all those other three professions I mentioned have, and as our profession has, as becoming a licensed professional engineer. In fact, in some states, Texas notably, you're not actually legal to have engineer after your name unless you are a licensed professional engineer. So I want you all to strongly consider, while it's all fresh in your mind, taking that Fundamentals of Engineering exam and pursuing an opportunity to work under a licensed professional engineer during the next 3 to 5 years, so that you have the opportunity to take and pass the professional engineering exam in your field and in your state. So the Order of the Engineer was initiated in the United States to foster a spirit of pride and responsibility for our profession, to bridge the gap between the training that you are starting to move out of as at least a full-time job. You'll still always be learning, and your experience that you're going to start to gather quite a bit of. And then also, as a way to present to the public a visible symbol, the ring, identifying you as an engineer who have taken this oath. It's amazing the number of times I'm in the airport and somebody comes up to me. Usually the first question they ask is if I'm Canadian, because this originally started out of the Canadian, out of Canada, with Canadian engineers, and I would say almost all the Canadian engineers take this oath and get the order. One of the interesting distinctions between a Canadian ring and an American ring is the Canadian ring is serrated, where our ring is smooth, but otherwise they're very similar. So I want to talk about the story that got all this started, because as I mentioned to you, this is a really important, there's a lot of messages in this story that I think you really need to understand. So the Quebec Bridge and the failure of the Quebec Bridge is what caused the Order of the Engineer to get started. The Quebec Bridge is a riveted steel truss structure, about 3,200 feet long, about 95 feet wide, and about 341 feet high. This is a big bridge. Cantilever arms of around 581 feet support a central span that's 1,800 feet. That's the longest cantilever bridge in the world, still today, over 110 years later. In 1903, the government of Canada vigorously promoted this project because it wanted to see the National Transcontinental Railway from Montcalm to Winnipeg throughout all of Canada. So as part of its commitment to this project, the government guaranteed a bond issue to pay for it. And the Phoenix Bridge Company's design, it was one of the competing companies, called for a cantilever bridge, 150 feet high, above the high water mark, which was 341 feet. And the structure would have a cantilever attached to piers on each side of the river by anchor arms of 500 feet, with a center span initially projected to be 1,600 feet. The Quebec Bridge Company selected a person named Theodore Cooper, a well-known American bridge designer, as the chief consulting engineer, very experienced engineer. Choice seemed ideal because when it came to professional construction designers, Cooper had few equals on the whole North American continent. He endorsed the design from the Phoenix Bridge Company as being the best and the cheapest. Although he decided to lengthen the center span from the designed 1,600 feet to now 1,800 feet. Now, before parts of the bridge's superstructure were manufactured, the company, design engineer Peter Slapka, estimated the weight of the completed work. These are the people that were actually building the bridge. The Canadian government wanted to have someone else double check all the weight calculations, but Cooper, a lead engineer, objected to that and essentially approved, the Canadians approved the plans without alteration. But then in February 1906, Cooper became concerned when he examined the detailed drawings of the Phoenix Bridge Company, which he should have done earlier, and found that the actual weight of the manufactured steel parts far exceeded the weights estimated by his engineer prior to manufacturing. But by then, the south anchor arm, the tower, and 2 panels of the south cantilever arm were already in place. Cooper decided to forge ahead and not introduce any changes. Do the calculations. If you find a mistake, stop. It might be expensive. You may lose your job. You may lose your license. But that's how we should work as engineers. And if somebody wants to check your work, that's awesome, right? Just like being in class. Somebody says, hey, can I check your work, see if you didn't make any mistakes? Right? They know what they're doing and they did their work. Why not, right? Why would you not want someone to make sure, especially on something this important and this leading edge? Remarkably, Cooper, who claimed he was not in good health, worked out of his New York City office and did not make visits to the site of the erection of the superstructure. He relied on Edward Hoare, the chief engineer, whose largest bridge that he ever worked on was 300 feet. Okay, that's a very small bridge. And Norman McClure, who just graduated the month before, much like yourself. The inspecting engineer for who is listed then as the inspecting engineer for the Quebec Bridge Company. And he told them, hey, keep me informed if you see anything. Well, first of all, for the 2 people that are only on site, one to have just graduated and the other one whose biggest bridge was 300 feet, it's really, really important to know your bounds and to get help, to ask for help. If you're put in that position, no matter what it is, there's nothing wrong with basically recognizing that this project might be a bit outside of your current skill set and experience set, and you need some more personal assistance. In June 1907, McClure told Cooper that errors of alignment in some of the lower cord splices on the bridge's south arm had to be corrected by jacking them into place, which is not normal in bridge construction, I understand. They did mention that to Cooper, and his reply was, make as good work of it as you can. It's not serious, but please draw attention in the future to make sure that the members were built correctly. In other words, his assumption was that it was sloppy work on the manufacturer. He didn't consider the other possible options. Look for the signs. Don't assume, especially given the information that had already gone before in this situation. In August, McClure telegraphed New York because splices between some of the lower cords in the south arm now were bent. Disturbed by this report, Cooper asked for further details on how they became bent. The misalignment of one of the lower cords became very noticeable, and in just 1 week, one of the cords, called 9L, went out of line from 3/4 of an inch to 2 1/4 of an inch. But despite these and the other irregularities, the Phoenix Bridge Company did not halt construction. Acting on Hoare's advice, McClure did go, he traveled to New York City to brief Cooper personally about these difficulties. After their meeting, Cooper telegraphed the contracting company in Phoenixville as follows: add no more load to the bridge until after due consideration of these new facts. McClure will be over at 5 o'clock. Now, Cooper believed that that same message would also be forwarded to the site, but this never happened. Further, after talking to McClure, Cooper assumed that work on the bridge had stopped, but no one bothered to validate that, and it hadn't stopped. That was not the case. Obviously, if there's something that's really important, not only do you need to take expedient action, but you have to follow up. If it's really important, always follow up. Never assume. So later that same day, McClure met with Phoenixville Bridge Company officials in Phoenixville, and after some discussion, it was decided that they should reconvene the following day. However, on that day at 5:37 p.m., August 29th, 1907, around the same time their meeting was ending, the Quebec Bridge suddenly collapsed. In the space of 15 seconds, the south anchor arm, the cantilever arm, and the partially completed suspended span fell 150 feet into the St. Lawrence River. At least 75 of the 86 workmen on the site were carried to their deaths, and property damage was later estimated at over $1.5 million. Only 16 bodies were ever recovered from the twisted wreckage at the bottom of the river. It was Canada's worst bridge disaster. But worse. Elsewhere, about a dozen men who survived the fall were trapped alive in the mangled debris on the shore, which at that time of the day was relatively dry. But for these men and the rescuers, the situation became more frantic as the tide came in. The rescuers had less than an hour to save them, and they had no equipment. None of this was planned for. No safety procedures or contingencies were ever considered. Nothing was available on site. And while they tried very, very hard to get the men out, as the water level rose, the trapped men drowned. The Royal Commission, which investigated the cause of the disaster, concluded that the failure of the cords was due to their defective design. The Commission attributed this to errors of judgment on the part of Slapka, the design engineer, and Cooper, the consulting engineer. The Commission found that grave error was made assuming the dead loan for the calculations at far too low a value, and not afterwards, once they had the proper evidence, revising their assumptions. The error was of sufficient magnitude to have required condemnation of the bridge. In spite of the enormity of this accident, the federal government did decide the project must be completed to keep this rail link going. In April 1911, the Board of Engineers contracted St. Lawrence Bridge Company of Montreal to take basically a similar but modified design of the cantilever bridge. One important innovation that added strength to the bridge was a new design called a K-truss. The feature was conceived by the president of this company. Construction started in 1903, and eventually the two approach spans, the anchor arms, cantilevers went up on both sides of the river. By 1916, the bridge was nearly completed. Indeed, all that remained was the job of hoisting the mammoth center span that would be connected to the cantilever arms. The 5,100-ton span was maneuvered into position between the arms using huge lifting hangers attached to both ends, raised by hydraulic jacks. Span was to be lifted 2 feet at a time in a repeat operation. South end, north end, south end, north end. After 4 successful lifts on the north end and 5 lifts on the south end, the southwest corner of the span tore away and sagged. A few seconds later, the other ends pulled off their supports and the whole span came loose and disappeared in the river with 13 men who were also carried to their deaths. Once again, the cause of this disaster was poor planning, poor design, and poor operational rescue contingency design. They did finally complete the bridge with no further loss of life, and it now still stands today. But I think it's really important to understand all the mistakes that were made and the seriousness of those mistakes, because you yourself may be confronted in similar situations, and I want you to strongly consider what happened here, what the foundation was of your oath, so that we never ever see this happen again. So the Iron Ring legacy is called, at that time, the ritual of the calling of the engineer. The words, hope I'm not doing that. About that? Yeah, that was weird. Thank you. Okay. The words of the ritual written by the British author Rudyard Kipling, who had high regard for engineering. And the ritual includes the placing of a ring on the little finger of the working hand. During 1966, a group of U.S. engineers began to pursue the establishment of what was then known in Ohio as the Order of the Engineer. The first ring ceremony was held on June 4th, 1970 at Cleveland State. Since then, the Order has grown to include tens of thousands of members, like yourself, inducted at links established in nearly every state in the Union. The first Iowa State Order of the Engineer ceremony, as we're doing it here for the undergraduate group, was done in December 9th, 2002. At that time, there were 42 graduating engineers who took this obligation. One of the changes that was made around that time is to offer all graduate engineers from accredited institutions the opportunity to become members of the order. Prior to that, such as when I took the oath in 1992, it was only opened when you got your professional engineering license. At the second ceremony in 2003, Iowa State first used its own ring and ring base, which we now have. The ring itself was developed at Ames Lab, and the ring base was made by the Thomas Rizicki family. The Engineering Student Council of Iowa State is proud to continue this tradition of the Order of the Engineer, and at our university in celebration of both engineers past and present. And we really do congratulate you, as Dean Easterling mentioned, on taking this obligation today, on joining this order, and on making this promise to the service of our profession. The Order of the Engineer, to which you'll soon belong, is an independent organization. The purpose is to foster a feeling of pride and dedication to our profession, which binds us together. And we ask you to accept and interpret very seriously and with pride the meaning and purpose of this ceremony to which you're about to subscribe, and to uphold these standards and to maintain the dignity of our profession. The order is symbolized by the acceptance of this obligation and the wearing of the stainless steel ring on the little finger of the working hand. The order is not a membership organization. There aren't any meetings to attend or dues to pay. Instead, the order fosters a sense of unity and purpose and the honoring of your pledge lifelong. The significance of what you're about to say and do might be best expressed in this way. You're going to say, I'm an engineer, and I have an obligation. My obligation has become my desire. And I want to remind you that as an engineer, you're an engineer not just from 8 to 5. You're an engineer when you're working at your church or your clubs or some nonprofit organization. Everywhere that people need an engineer, you're the engineer, and you are basically representing all of us in that capacity. This isn't just a job. This is a lifelong profession. It's your obligation. So your desire is to apply this golden rule, our code of ethics, to the technical knowledge of this world by persuasion. Your desire becomes the yardstick of your professionalism. And lastly, that your professional means you'll never ask yourself, how much do I get out of it? But rather, how much can you give? The symbol of the desire to be a giver is the engineer's ring that you should wear for all to see on the pinky of your working hand. Originally, the rings were not stainless steel, so they would rust if you weren't working regularly, but of course that could kind of create a mess in your hand, so we went to stainless steel. The ring will say to all who see it, here's an engineer possessed of a publicly avowed dedication to their profession and the public they serve. So after accepting the obligation, you'll be presented with your ring. You're to wear it so that it will remind you every time you sign a set of plans, contract documents, design specs, of this obligation and faith that you are taking here today. Each of you must possess an engineering education and are willing to subscribe to this engineering code of ethics. You'll now be invited to join this order and accept your ring. You must accept the obligation seriously and with pride in both yourself and your profession. And please consider these words carefully, and remember always that our special knowledge carries with it the obligation to serve humanity with complete sincerity, with complete honesty and complete integrity. We can never anticipate all the challenges we're going to face as we work on our designs, as we manage our projects. But we're bound to foresee and plan, contingency plan, all that we can to keep the public welfare upmost in our minds. On behalf of the Order of the Engineer and the various members of the College of Engineering, I invite all of you now, please, to stand up. We'll be reading these red words. So you can please follow after me and speak aloud the words of the obligation. I am an engineer. In my profession, I take deep pride.
To which I owe solemn obligations. As an engineer, I pledge to practice integrity and fair dealing, patience and respect, and to uphold devotion to the standards and the dignity of my profession, conscious always that my skill carries with it the obligation to serve humanity by making the best use of the earth's precious wealth. As an engineer, I shall participate in none but honest enterprises. When needed, my skill and knowledge shall be given without reservation for the public good. In the performance of duty and in fidelity to my profession, I shall give my utmost.
You may now be seated. Let this ceremony always remind you that professional ethics with its associated commitment to public safety and welfare comes before all else. Congratulations, and please come forward as your name is called to receive your ring and your certificate.